Yeah, this is where we have stopped in the previous class. I think I have discussed about this, the potential pH diagrams, which are very important in getting the directions of the corrosion, whether to prevent it or to excel. So how do I prevent or how do I excel? Because I could vary the two parameters, the pH on the x-axis and potential on the y-axis. Okay. So that you can come to have three zones, where either immunity zone or corrosive zone or passive zone. So what is immunity zone? Immunity zone is where your metal is stable, so it never corrodes. So if you are in that immunity zone, you are safer enough. Your metal will never corrode. But if you just vary either the potential or the pH, you will fall in either the passive zone or in the corrosion zone. So what is corrosion zone? Where the metal ion is thermodynamically stable. That means your oxidation is predominant. So the zone where corrosive, if it falls, the potential pH, if it falls in the corrosive zone, definitely the metal ions will be stable. So oxidation is predominant. If suppose if we are falling in the passivity zone, what is the meaning of this passivity zone? Where metal oxide is stable. So definitely there will be a metal oxide form, and which tries to always hinder, or it tries to always not allow the oxygen to interact with the fresh surface. So that what will happen? Your corrosion is prevented by forming the oxide layer. So oxide layer formation will be in the second zone. Okay. But there are certain limitations, as I told in the last slide. What are those limitations? These diagrams, these EHPH, or other names are called pore batch diagrams or electrochemical phase diagrams, does not include the impact of the kinetics. So what do you mean by those things? These diagrams are not taken into account of the kinetics part. What are the kinetics part? Kinetics in the sense the rate of reaction or the influence of temperature. Fine. So there are, because temperature will also increase the corrosion rates. We have seen increase of velocity, increase of concentration. We have seen all those things. All those parameters will fall under the kinetics, but these diagrams are not taking into account of those kinetics. Fine. What are it takes into account? It takes into account only the pH and then the potential, and then it is taking at a constant temperature of 25 degrees centigrade or 298 Kelvin, and concentration of 10 power minus 6 moles per liter. That is what it is taking into account. Okay, so that is the first limitation. It is not taking into account of the kinetics. What is second limitation? It presents only one predominant species. So it taking into account of only one species, that is I told you 10 power minus 6 concentration it assumes. The last one is it depends on the accurate thermodynamic data. Because see, the phase diagrams always takes into account of the thermodynamic data. So this also takes this account of those things. So definitely it is depending on the thermodynamic data. If the thermodynamic data is wrong, the phase diagrams which has built up is wrong again. Fine. So that is what the three most important limitations of these diagrams. Okay. Let's go to the next concept. The next concept is factors affecting the corrosion. We already seen the corrosion is predominant in certain environments. Certain factors will associate, will enhance, or sometimes will inhibit. Now let us look at each parameter in this class so that we come to know whether to control certain parameters will inhibit the corrosion or not. So what is the first thing? First thing is the nature of the metal. See, whatever the metal we choose in the periodic table, all the metals will not undergo corrosion at a similar rate. True or false? Will all metals in a periodic table will undergo corrosion at a similar rate? Definitely not. If I take iron corrodes at a different fashion, different rate, than if I take either gold or platinum, which are also metals, they never corrode. They never form oxides. Fine. So every metal does not lead to the same tendency of getting corrosion. That is what the nature of the metal. The metal nature will tends to change the corrosion behavior. So what is the first parameter? The first parameter is in the nature of the metal. Position in the galvanic series. We already seen the galvanic series or electrochemical series. Is the position will affect the corrosion? Is the position in the electrochemical series will affect the corrosion? Of course, what we study in the electrochemical series, the series has been built up in the decreasing values of standard E naught, standard action potentials. So what we have come to know from the table, the metals which are above in the series will be acting as anodes are very active. The metals which are below in the series will be acting as cathodes or inert. So the metal which is tending to move up, what will happen? Metal tending to moving up, what will happen? So the metal, the greater the oxidation potential, the metal is higher up in the galvanic series, greater is its tendency to become anodic, and hence greater is the rate of corrosion. It's true, na? So which are going up will definitely will become very active, very anodic. So very high oxidation rate, so highly corrosion. Fine. So that is what the first thing. Position in the galvanic series. Now what is the second one? Purity of the metal. So what is purity? What is purity? We often talk about the purity of gold. How do you measure the purity of the gold? In terms of carats. So 24 carat gold, 22 carat gold. What it signifies? It signifies how much percentage it is the purest form. See, gold will not be in 100% gold. If you take any gold, you will never get 100% gold. You will add something else. Why we will not take 100% gold or 100% silver? I told you in the material science class. I suppose that I took the class for your batch. Is it for your batch or your juniors? Your juniors. Your batch only, no? So I discussed why silver is not 100%. The silver ornaments we wear, it's not 100% silver, because what will happen? They will be fragile. They will break up easily. In order to improve the strengths, workability, in order to improve the hardness, strength, we add certain other metals into the silver or gold. So that will increase the lifespan, longevity, or hardness or brittleness. So the other parameters will be improved if we add some other metals. That's why we will take gold not in the purest form. We will add some percentage of very small ppm levels of copper we will add, because gold should be strong enough. The purest form of gold is not strong again. Similarly, if you are not in the pure, you are more tending towards the corrosion. 100% pure never corrodes. But if a small percentage of impurity comes into picture, what will happen? That impurity will be leading to heterogeneity. The surface will become heterogeneous mixture, and these heterogeneous mixtures will form individual electrochemical cells inside the metal. So these individual electrochemical cells will tend to form more corrosion sites. So more corrosion will take place. Okay. So what is the second parameter? Second parameter is the purity of the metal. The more impure, more corrosion. More pure, no corrosion. Understood? So any small percentage of impurity in your metal, your corrosion will be much increased, because that the small impurity will increase the heterogeneity in the mixture. So those heterogeneity will increase the local electrochemical sites. So those local electrochemical sites will enhance the corrosion rates. So that is second point. Third one is the physical state. See, the physical state is also very important, because if we look at the physical state, see, the smaller the grain size, the more will be the corrosion. Right? Smaller the grain size. See, always I took this example. If I take two glasses of water, if I add in one glass sugar powder, if I add one in another glass sugar cubes, which will be fasterly dissolving or solubilizing? Sugar powder rather than sugar cubes. Why? Because sugar powder is having more surface area per unit volume than the sugar cubes. Okay, so more surface area means more active, more solubilization, more dissolution. So highly active if the surface area is more. So if surface area, when it will be more, if it comes to very small fine sizes, because fine sizes will have more surface area. So smaller grain size will be leading to high activity, because high dissolution, high solubility means what? High active. So the smaller the grain size means More active in the sense. So more active means more oxidation, so more corrosion. So the physical state is also very important. Understood now the third point, physical state. Now what is the fourth point? Nature of the oxide film. See, the when I took any metal, the formation of the metal oxide layer or the oxide film will always be there. Some metals, this oxide layer will be peeled off. For some metals, it will be stagnant layer. For example, the case of silicon. Silicon will be the silicon oxide, which we call as the silica. That is a form layer. So it will never pass the electrons or oxygen to enter into the silicon surface. That's why once silicon is formed, silicon oxide, it will not work at all. That means a form oxide layer will be formed. For some other cases, oxide layer will be formed, but it will be peeled off quickly. Best example is iron only. Iron slightly extended forms iron oxide, but iron oxide will be quickly dissolving. So it will never be as an oxide layer. It will be removed off easily. That's why again fresh oxygen will come. Again corrosion will take place. So this oxide film nature is also very important. If my metal is forming strong affixed film, then you can prevent the corrosion. If the oxide formed is quickly removed either by the passage of the velocity, the fluids or whatever it may be, if it is peeled off, then what is the need? Again, you will be undergoing the corrosion. Okay, that is the nature. Now, the last point is related to areas. We studied the surface area effect. What is surface area effect? Surface area effect we studied. SC by SC ratio. IA is equal to SC by SA into IC. What is this SC by SA ratio? Amplifying factor, Flint factor. So what it signifies? More SC by SA ratio leads to more IA. More IA means more corrosion current. That means more corrosion. So always we have to design such a way that this SC by SA ratio should be as less as possible. SC by SA as less as possible means either SA should be less or SA should be more. What is SC SA? Surface area of the cathode, surface area of the anode. So we always have to design such a way that the surface area of the cathode and surface area of the anodes are such that this SC by SA should be always minimum. So that is what the relative areas. Because the areas also plays an important role which is affecting the corrosion. Clear? The next point is the solubility. Solubility is also important because we have seen the four cases. Four cases in the first, maybe second class. What are the four cases? I dipped a nail in a tube. I put some water. So four cases I have studied. What will be the case with the sodium chloride is added? More corrosion. More corrosion at the same time we observed the particles have been coming onto the bottom. So why it has come? Why it has come? Because the oxide, whatever the corroded product is solubilizing. It is soluble and then coming onto the surface. So what will happen if it is soluble and coming onto the surface? Again, fresh surface is exposed to oxygen. So again, more corrosion. That's what I'm saying. Iron may form iron oxide, but this iron oxide film will be quickly peeling off from the surface. That's what the nail we have observed. The more corrosion takes place because of the sodium chloride there. The sodium chloride will acting as a electrolyte. Fine. The chlorine ions is again highly oxidizing agents we have seen in the electrochemical series. So this chlorine, they try to form a good electrolyte system. Passage of ions, electrons will be much more. So more corrosion. More corrosion means more surface will be corroded. More corrosion at the same time this corrosion product is soluble. So if it is soluble means what? It quickly dissolves in the and it comes to the bottom. So another example given is lead in sulfuric acid. What it forms? Lead in sulfuric acid forms lead sulfate, which is insoluble. Hence corrosion will be smaller rate. So there is a specific case. Sometimes solubilization, see in this case it will not soluble. Whatever the lead sulfate formed, which is insoluble. But in case of iron, soluble. That's why it is coming to the bottom of the tube. Okay, that is another parameter. The last parameter is the volatility. That is also one parameter, is it not? See, whatever the product formed, corroded product formed, if it is volatile, what will happen? What will happen? It evaporates. See, already see corrosion takes place. Now this surface is corroded. Now this corroded product is volatile. What will happen? It just evaporates. Then if it evaporates means what? Again fresh surface is exposed to oxygen. Fresh surface is exposed to oxygen. So oxygen will come, water is there, again oxidation takes place. So volatility increases, corrosion increases. You get now? So seven important factors: volatility, solubility, and then what is the previous one? Surface area effect. Next one, nature of the film. Nature of the film. Next, physical state. What is physical state? Smaller grain size, more active B, more active, more corrosion. Purity, more impure, more corrosion. Because the impure metal will be increasing the heterogeneity. Increasing the heterogeneity means more localized sites. More localized sites means more electrochemical cells are forming, more corrosion. Position, higher up in the series, highly active, more corrosion. Clear now? So those are the important factors affecting the corrosion. Now look at the nature of the corroding environment. See, corroding environment is also affecting the corrosion. Is it not? We have seen the parameters we have seen. Let's take the temperature. What will happen for the temperature case? If temperature increases, what will happen? What will happen? See, we have studied in kinetics. The temperature increased. The rate of effective number of collisions will increase. More collisions, more reaction rates. So here, what is the reaction? Reaction is electrochemical oxidation, that is corrosion. In our case, electrochemical oxidation is the reaction. So when temperature is increased, the molecules get energized. So they will involve more in rapid collisions. So these effective number of collisions, what we call the frequency factor, will be increased. So the reaction rate will be increased. So that is what the temperature effect. The second one, humidity. Will humidity play an important role in corrosion? Of course, because we have seen. See, we will never plan anything near to the seashores. The main reason is seashore having more number of ions in the atmosphere. Chlorine ions will come out of the surface from the seashore. Sulfate ions will come. Magnesium ions will come. Sodium ions will come. So all these ions will try to be very active in their oxidation states. So they will act as highly oxidizing agents. They try to pull the electrons when our surface is available. Because my surface is always losing. Because iron thermodynamically unstable. It tries to lose. You cannot stop iron to donate the electrons. Is it? Can we stop? Thermodynamically, it is that Gibbs energy is negative for iron. Iron will always lose electrons. No one will stop iron to lose electrons. Iron will be in Fe2 plus state or Fe3 plus state only. Fe losing 2 electrons or 3 electrons to form Fe2 plus or Fe3 plus. No one will stop iron to lose electrons because it's thermodynamically unstable. So it wants to be in stable position. If you look at the E naught value corresponding to the Gibbs energy value. So when it loses, if someone is there who is picking electrons, then the rate of this reaction is very fast. Here chlorine is available, highly oxidizing. It tries to pull the electrons. So here losing electrons, here chlorine is picking electrons. So chlorine ions, fluorine ions. So this humidity, even the small point of moisture, what will happen? This moisture will be acting as a solvent. This moisture in the air acting as a solvent for either oxygen or H2S or sulfur dioxide or sodium chloride, so that it forms a good electrolyte system. Good electrolyte system means good passage of ions. It is giving the directions for the movement. The diffusion will be much faster in place of humidity. So in place of humidity, this whatever the moisture, maybe small percentage, will acting as a good solvent for the oxygen molecules, H2S molecules, or sodium chloride molecules. So it will form a good electrolyte system. Good electrolyte means good ionic movement. Good ionic movements means more corrosion. Is it okay? The effect of pH. pH effects or not? pH effects. That's what. See, many metals will corrode in acids only. In acids only means more. In acid means less pH values. Is it not? Because more H plus ions are available at less pH. pH reference is minus log H plus. So any metal you take, either you take stainless steel, that will also get corroded in place of acids. We have seen the examples also. 16 chromium, 8 nickel. In nitric acid will get corroded. In sulfuric acid get corroded. So this pH will also get affected with your environment factors. Now presence of impurities, we just now said, the impurities will acting as the impurities. Impurities will increase the heterogeneous sites. In other words, the impurities in the atmosphere, what that is what impurities in the metal. Now impurities in the atmosphere, what it will take? See, in the atmosphere, what are there? In our atmosphere in the classroom now, there are a lot of carbon dioxide molecules are there, lot of nitrogen molecules are there, lot of H2S molecules are also there. Right? So what will happen? These are all impurities. You look at the line what I have written. The corrosion of metals is more in areas near to the industry and sea, because sea only will give more number of impurities in the air. This is due to the fact that corrosive gases like sulfuric acid, H2S, SO2, CO2, and fumes of H2SO4 and HCl in the industrial areas and NaCl of seawater leads to increased conductivity of the liquid layer in contact with the metal surface. Okay, so the conductivity, that is what I am saying. It will form a good electrolyte system, increase acting as a good solvents. Fine. Now, presence of suspended particles in the atmosphere. Suspended particles, as chlorine ions, they will act as a good electrolytes. See, strong electrolytes. Fine. So these are all points in case of nature of the corroding environment, and the previous all points nature of the metal, whether it is up in the series, whether it is purity or not. Okay. So all comes under the nature of the metal. Okay. Now, fine, understood. This is a very important question in this unit. The factors affecting the corrosion. So either you talk about the nature of metal, the factors, or you have to study the nature of the corroding environment. The classification of corrosion we already discussed once. So there are three ways of classification. As I said, depending on the temperature, depending on the aqueous medium, wet corrosion, dry corrosion. What is wet corrosion? What is wet corrosion? Corrosion taking place in the aqueous media. That's what called wet. What is dry corrosion? Non-aqueous media, which are called dry. Fine. So I given some examples also. If you look at, see here, wet corrosion occurs when a liquid is present. This is usually involves aqueous solutions or electrolytes and accounts for the greatest amount of corrosion. A common example is corrosion of steel by water. Why corrosion of steel will be water? So even if I dip the stainless steel in water, that stainless steel also get corroded because because water contains H plus ions. H plus is also good oxidizing agent because H plus puts the electron. H plus electron gives H2. We have studied standard reduction reaction. So water will also trying to corrode the stainless steel. So which is in the aqueous medium. That's why it comes under the wet corrosion. So what is dry corrosion? In absence of liquid phase. So maybe see vapors, gases are usually the corrodants. Dry corrosion is often associated with the high temperatures. An example is attack on steel by furnace gases. So whenever the industrial furnaces, they lose some flue gases out. Those gases will attack the steel. So which is an example for dry corrosion. Okay, vapors or gases will be dry corrosion. Now I also kept some one more example here. Wet chlorine, dry chlorine. You see the example here, the last one you just go through. The presence of even small amounts of moisture could change the moisture effect. You see the moisture effect. For example, dry chlorine is practically non-corrosive to ordinary steel. But moist chlorine or chlorine dissolved in water is extremely corrosive and attacks most of the common metals. Look at the sentence. So dry chlorine is almost non-corrosive, but small percentage of chlorine dissolved in water, that's called wet chlorine, is highly corrosive for steel. And another thing is for titanium, that is a reverse case. For titanium metal, Dry chlorine is highly corrosive rather than wet chlorine. Reverse case, see, dry chlorine gas is more corrosive for titanium metal. So we have to be very careful in our industry, in our equipments, instruments, wherever we are, whether that material is made up of titanium or magnesium or steel or iron. Accordingly, we have to design the other things, because in the environment we have to look at whether my environment is wet chlorine gas or dry chlorine gas or any other factors are there. I have to clearly see. Fine. So let's come to the most important classification of corrosion, though there are different classifications, but the one Fontana always writes or discusses the forms of corrosion as eight forms. Eight forms of corrosion. So these are the eight forms: uniform or general corrosion, galvanic or two metal corrosion, crevice corrosion, pitting corrosion, intergranular corrosion, selective leaching or parting corrosion, erosion corrosion, and stress corrosion. So these are eight forms of corrosion. Now, if I in a broader way, if I write corrosion as a uniform or localized. What is uniform? What is localized? Uniform means across complete surface if corrosion is taking place. That's called uniform. So if let us say this is my metal. Now if this metal is completely all areas have been corroded, that's called general or uniform corrosion. Or localized. Or only specific site is getting corroded. Selectively, this site only corroded, this site is only corroded. It's called localized corrosion. Now come to the localized corrosion, because that is very important corrosion. Why I am saying localized corrosion is very important? Because see, localized means what? At a specific site only the corrosion takes place. Sometimes we will miss that specific site. See, let us say if it is at the center, people will always look at the center, fine, no problem. They can take measurements. They can try to prevent. But let us say corrosion has taken place at very back end, maybe at smaller site like this here. So you will miss that place where the corrosion has taken place. So if this is the place where corrosion is taking place, means what? It will crack, increase, and finally destroy. So this localized or specific site selective corrosions are highly dangerous. Highly dangerous. Now, what is the classification again in the localized? Either macroscopic or microscopic. Now, what is macroscopic? What is microscopic? Macroscopic. That means at least we can visualize with our eye. Macro, bigger size, little bit bigger size. No, micro. You cannot see from your naked eye. You cannot see. So you need some electron microscopes or at least optical microscopes in order to visualize the corrosion sites. Fine. So what are macroscopic? That means you can visualize galvanic. Galvanic you can see now. We have seen. What is sacrificial anode method? We are dipping the magnesium rod or the iron rod, iron pipe. So here we are observing whether my magnesium rod is corroded or not. If it is corroded, I remove that magnesium rod, throw it out, put another magnesium rod. That means you can visualize, you can see. That's why it comes under macroscopic. Clear? Galvanic, erosion, crevice. But look at microscopic. You cannot look at unless otherwise you need some microscopy instruments to visualize. Intergranular. What is intergranular? I have to look at the granule size. As I said here in the previous case, the nature of a metal. If the grain size is very small, more corrosion, because the grain size more small means more active area, more surface area, more active, more corrosion. So I have to look at the intergranular states. That means what? I have to go inside the structure. I have to look at the structure, what this type of structure it is. Either it is FCC, BCC, whatever may be the structure it is. What could be the intergranular places, interstitial positions you have seen in the metal science. So there, this corrosion takes place. stress corrosion. Fine. So let us look at each and every corrosion, because this may be a lengthy question or it may be given in a breakways questions, because sometimes they will ask in a one question write all eight forms of corrosion, or sometimes they will ask only write only two, maybe these two corrosions with examples and diagram. So let us learn one by one. This is another classification that is based on the ASM. ASM is American Society for Metals. So let's come to the uniform corrosion. As I said, what is uniform corrosion or general corrosion? It's completely, the surface is completely corroded. Look at this example. So chemical or electrochemical reaction that proceeds uniformly over the entire surface, over large area, but it is relatively slow and predictable. See, if you go to maybe ships, you can see these type of corrosion crossing entire surface. But it is surprising. This has corroded over years, not in a day. This corrosion has took place over years. That's why the corrosion is very slow, because it has to cover the complete surface. Is it not? It took a lot of time for entire surface to get corroded. So relatively slow. Easily corrected with coatings and regular maintenance. So this corrosion can be easily prevented. That's why many, if you see ship marines, they'll always coat with the suitable painters, suitable paints. So it can be easily. What are the examples? Steel or zinc in sulfuric acid. Iron in all environments, uniform corrosion only. Tarnished silver. What is tarnished silver? Black color. First example I showed you. Silver becomes silver sulfide. Prevention we will look at. Prevention methods are there. We will talk about separately the all preventive methods. Okay. Galvanic corrosion we have already seen. What is galvanic corrosion? When two dissimilar metals are in getting contact, the metal which is in the upper in the series will always become as an anode. The metal which is in the below series will always become as a cathode or inert. So the metal which is above in the series will get corrode by sacrificing to the cathode. That's why iron will be protected when I connect with either magnesium or zinc. Okay, so iron magnesium couple or zinc iron couples, iron will be getting prevented by sacrificing this magnesium or zinc, called galvanic metal coupling. Okay, so we have discussed all these things. So I am not stressing more time here. So I showed you some of the examples: zinc with steel or tin with steel. Zinc with steel. Zinc is zinc. You have to understand the position of the zinc and steel. That means iron. Position of zinc and iron, position of tin and iron. So we have seen in the relative surface areas which is anode, which is cathode. If you know which is anode, which is cathode, you are done. So which will be getting corroded, which will be prevented. So I give a lot of examples I have given. See, these are all very good examples if you look at. See, knowingly or unknowingly, we are using a lot of foodstuffs, lot of food packing materials, but the inside principles are missing out. So I always get connected with the nature's examples. So this is just a left to you. You think of why I kept this figure. I do not want to explain. Now this galvanized steel. This is what I told you. The zinc is protected. Iron is protected by corroding the zinc. So zinc galvanizing. So these are all iron covered with the zinc coatings. So this iron nail will be prevented. So this is called zinc anodizing. Ship hulls, etc. So series, galvanic series, we have discussed all these things. So let us not worry about at this point the prevention, because I will again deal with the prevention methods in a specific class. So this is all sacrificial anode we have discussed. So we'll talk about this anodic current and everything in later classes. Let us mainly get back to the other form of corrosion. So third form of corrosion is erosion corrosion. Look at the name erosion. What is erosion? Eroding the surface. Fine. So it is the deterioration of the metals and alloys due to the relative movement between the surfaces and the corrosive fluids. See, if there is a metal is here like this, let us say this is the metal. Now let us assume I have some corrosive fluid in and around this metal, and this corrosive fluid is moving at much faster rate onto the surface. What will happen? There is a relative movement of the air or the fluid which is passing to the metal surface. There is a relative movement. So this high velocity of the fluids, what will do? It will try to erode the surface. They will take off the surfaces. So what will happen if it is taking the surface means it is for let us for time being assume this metal has a metal oxide layer. What will happen if my corrosive fluids are moving at a very high velocity near the surface? It tries to remove this oxide layer because of high passage of velocities. So my metal is now does not have the oxide layer. Again, it will get corroded. The surfaces will be eroded. You observe the rotors. Why rotors will get corroded? Because they move with very high velocities. They move with very high velocities, so there is a relative movement between the fluid and the surface. So that's why it will get corroded. So best examples are you look at here. I give example. You see, piping, propellers, turbine blades. In mechanical operations, you have seen the turbine blades, agitators. So why agitators will get easily get corroded? Because it gets more velocities, more relative movements between the surface and the fluid. It tries to erode the surfaces. వేరుశనగకాయ తీసుకున్నాం అనుకోండి ఇట్లా ఇట్లా అంటే ఏమవుతుంది I'm rubbing means what? I'm making a relative movement between that what we take in the grain and with my surface. I'm just doing like this. So this type of rubbing action will try to remove the surface peeling. Erosion. It is eroding the surface. Fine. So this is the example, and these are the solutions we will think of what to do. The best. What is the best solution? You tell me. See, when my surface is eroding, the corrosion is called erosion corrosion. Now, what is the best solution to prevent? Minimize the velocities, change the design, eliminate fluid turbulence. See, why we increase the more velocities using agitators? Because we want to increase the turbulence, because we want uniform mixing. But what will happen if more turbulence, more relative movement between the surface and the fluid? More relative movement means more erosion. More erosion. That is what I am saying. See, we will think in a very broader sense that if I increase the velocities, if I increase the agitation speeds, my production yield may be more. But you are looking at the production yield, but you have to think of the other consequences. So as I said, more agitation, what will happen? What is the polarization we talked about? Concentration polarization. So more agitation means more pushing of H plus ions. More pushing of H plus ions to surface means H plus ions will pick the electrons from the surface. So more corrosion. Or more turbulence means more relative motion. More erosion corrosion. Is it not my equipment is getting corroded here? Is it not my equipment is getting either my agitator is getting corroded or my equipment itself, metal which I am dipped is also getting corroded? What will happen over a long span of time? You have to replace either agitator or a blade, or you have to replace entire equipment. Is it not loss? That is what the first class with cost of corrosion. What is cost of corrosion? I have to replace all these things. Maybe a year or two, but later definitely because of the high velocities you are improving. In order to improve the yields or selectivities or conversions, you have to pay for it. If you won't think of what is my solution, what are the ions available, you have to pay for it. Clear? Crevice corrosion. Yeah, which time is there? So crevice corrosion, very very important corrosion because in order to identify or observe these corrosions, it took a lot of time. Usually, maybe I can show you. Yeah, first understand the mechanism, then I'll go back. See the flanges. You have you seen the flanges? This will be like this. In railway platforms, look at the flanges. So see, that means what? How the flange will look like? A metal with a half portion is linked with other metal with a half portion like this. That means half portion will be left. You like this. Maybe I can show you the next figure. Yeah, you look at the these type of joints have you observed? So you will observe in the railings two metals like this and they will be joined with some flange. Now the corrosion here takes place in this spot. This spot. That's why I have marked this diagram. I will explain you. So this is the spot where the corrosion will take place. Now can you identify whether this corrosion has taken place here? Can you observe? Because this spot is already clubbed with another metal, so this portion I cannot see. I can observe the portion here, or I can observe the portion here, or here. But I cannot observe the portion here. But this corrosion takes place at the joints. Between the two joints, this corrosion takes place. We will see what is the mechanism, how it takes place. You see, first understand what is crevice corrosion. It is intensive localized corrosion with crevices, shielded areas on metal surfaces. Localized intensive corrosion, localized I said you, localized. So it's not uniform, it's only some specific sites. Small volumes of stagnant corrosive caused by holes, gaskets, surface deposits. Now let us understand what is the mechanism here. See, when two metals are connected like this, see this is one metal, this is another metal. Let us for time being they have not joined, they have just like this. Later it will be joined, we will think of, but time being this is the metal, this is the metal, they have not joined, they are about to join. Now think of what is going to happen here. At this position, see this is a metal, this is a metal. Now if this is a metal, always metals will try to lose electrons. So this metal is losing electrons to form metal ion M2 plus. In case of iron, Fe2 plus. Now whatever the electron that is loosened will be residing on the surface. Is it not? Metal always having the loosened electrons until unless these electrons picked up by some other agent. Now let us assume I have water here, water and oxygen. Definitely will be there. In the moisture, there will be certain water molecules. In the environment, there is oxygen molecules. So these oxygen molecules, water molecules, they try to pull the electrons to form OH minus. We know the reactions, reduction reactions. Let me show you the reaction here. Yeah. So this oxygen, water will take the electrons to form OH minus. Fine. So there is a reduction reaction because we have seen zinc in aerated, zinc in non-aerated conditions. Why more corrosion in zinc aerated conditions? Because in aeration, oxygen molecule is also there, which will try to pull the electrons. Oxygen is also good oxygen agent. We have discussed a lot of things. So whenever oxygen and water molecules are there, they try to take the electrons quickly on the surface to form OH minus. Fine. Now let us think for some time. This all the electrons have been consumed to form OH minus. Sometimes what will happen? This place will be more positive ions. That means what? Now it requires some of the ions to balance that because the M2 plus ions are accumulating. Because the electrons are taken away here to form OH minus, quickly taken away because molecules H2O, O2 are there, they try to pulling the electrons quickly. So when pulling are taking place means more M2 plus ions are accumulating. That means more positive ions are accumulating in this place. After some time, what will happen if I going to get join here? There is no oxygen to enter, because if I leave like this, oxygen molecules can penetrate. But if I close, there is no oxygen molecules. So what will happen if I am stopping the joint like this? It is driving the chlorine minus ions to balance the positive ions formed here. So chlorine minus ions will try to get back to that place. Maybe I can think of, see more electrons taken by the OH minus. So certainly what will happen? Whatever the chlorine minus ions are there, they try to move into the surfaces. More chlorine ions will be getting into the spilling areas, because more positive ions are accumulating here. More M plus, more positive ions are accumulating. There is no oxygen passage because I have clubbed like this. So it will give direction for the chlorine ions to enter into those things. So more chlorine ions getting inside means what? More corrosion again. So this is what, if you look at the place, I just took this part and I have showed you. See, unknowingly, this entire portion of this metal, entire portion of the top metal will be losing. Now, can you identify if something is loosened here? Can you identify your name? Because that is happening inside the two metals. Slowly it is corroding. So ultimately what will happen? This entire mass is removed until it will become loosened. And if it is getting loosened means what? This contact will be slowly broken. Derailing. Understood? So this is very important mechanism. Whatever I explained the mechanism for the crevice corrosion. Almost similar mechanism is also there for the pitting corrosion. That is also similar mechanism. But this is very important. This crevice corrosion is also called concentration cell corrosion. Okay. Right? Again, combating we will discuss later. Fine. Filiform is also we will discuss. Now let us look at the pitting corrosion. This is also a similar sort of crevice corrosion, localized corrosion. See, local corrosion attack resulting from the formation of small anodes on a metal surface that produces holes or pits. See, whenever we observe any small hole is there, any small pit is there, corrosion will start at that hole or pit. That's called pitting corrosion. See, pitting corrosion results in the formation of pinholes or pits and cavities in the metal. Unknowingly, if any metal is left with many small hole, small pit, so corrosion will start there. That's why it is also called localized corrosion. It comes under the localized corrosion. So concentration gradients in the electrolyte cause some areas high in ionic concentration that can accelerate the corrosion. So you see, any unintentionally, if any small hole is left, small pit is left, again the principle what I tell the mechanism. More positive ions will attract the chlorine minus ions, and this more chlorine minus ions will try to increase the oxidation rates. This is what. See, more OH minus ions are formed. So more positive ions are formed, which is driving the chlorine ions to enter into the places, into the pits. So more chlorine ions enter, more corrosion will take place. Fine. This is what you can look at. No corrosion example. Complete metal is as it is. Pitting corrosion is any small pit is there. Corrosion will start, crack, and then remove the surface. So this part is completely removed because it looks like a hole pit. And then overall corrosion, that means overall if I left like this complete part is removed and then I am left with only this part. Okay. Prevention we'll look at later. Intergranular corrosion. Intergranular corrosion. So, as I said, whenever the grain size is very small, more active, more corrosion. That is inside the granules. So maybe I can show you the. You can see the figure here. You see the meaning of grain boundaries. We have discussed what is grain boundaries. Whenever we have atomic planes oriented in one direction and another atomic planes in another direction, and the line between these two orientations of the atoms is called grain boundary. The boundary demarcating the atomic planes of one orientation to another orientation. So, at these boundaries, because they are high energy regions, your corrosion starts. This is called intergranular corrosion. You can observe in case of steel. Steel, maybe perhaps I don't know how much they have showed you in the uh, when it comes from the furnace. So have you seen the iron steel coming from the furnace? Red hot iron. They have not shown. Okay, so when they have showed you, like visually, you can observe the red hot steel, how much it took for it to cool, and how they are molding. They are hitting with a large power. They will hit, and they will hit, and they will mount to whatever the shape we want. Because at that high temperature, only it will mold. When it cools, it won't mold. It won't mold to the desired shape what we want. So see, if any red hot steel is hidden with something, let us say this is the red hot steel. Let us assume, and the red hot steel, I have hidden with some instrument at this part, leaving this is not hidden. What will happen? What will happen? See, this entire part is red hot. Now I am hit with some hammer. Let us say for this part only. So I am hitting this part, but I am not hitting this part. What will happen? This part is under severe stress because it is hit with some hammer. But this part is free of stress. Is it not? There is a difference of a stress here. Is it not a difference driving force here? So this form of corrosion is called stress corrosion, because some part is under stress, some part is not under stress. So there is a flow of electrons, flow of ions, flow of movement from high stress to the low stress. Because high stress molecules, they try to move to low stress because they want to remove the stress. So during this passage, ionic movement will be there. You will be tending towards the corrosion. This is called stress corrosion. Okay. Yeah, this is what stress corrosion. You see. Have you look at this bending type of pipes? How they bend? See, usually any pipe will be almost horizontal. But if I want to bend means bend in sort of some U shape or this shape, V shape. How they bend? They will only bend in a red hot state. They will try to hammer it. They only this part, so that this part will be slightly bended. But this portion I'm not hitting because I want to be straight. I want to be straight this part, but I want to bend this part. So I will hit only this part only. So what will happen if I'm hitting means I'm making high stress, leaving this part unstressed. So there is a more movement of ionic movement, electrons or ions, from the high stress region to the low stress region. Because this part is entirely under high stress. This part is under low stress. So uneven stresses leading to stress corrosion. Or in another way, for example, let us take this type of pipe and let us send some fluid here, high velocity fluid. What will happen if this is the pipe? If I am sending high velocity fluid inside the pipe, so this fluid velocity, high velocity will try to go with high velocities until unless it is horizontal. But if there is some obstruction, because there is an obstruction here, sudden movement, sudden bend, what will happen? This high velocity fluid will suddenly strike the surface here because there is a bending is there. What it does, this high velocity fluid will try to erode this surface because it is hitting at a high velocity, because there is an obstruction here, there is a bend here. If there is no bend, fluid will go as it is, but there is a bend here, so this fluid will kick the surface, hit the surface, and try to erode, try to remove, peel off. Already it is under stress condition because it was hammered again. Now there is a high velocity going. That is why if you see any bending type of pipes will get corroded very quickly. This portion is completely eroded. You understood or not? Getting clear or not? If I send with high velocities, if there is a horizontal pipe without any obstruction, it will go like this. But there is a bend here, sudden bend. So this will hit the surface and then it tries to move down. High velocity come down, hit here, move down. So what will happen to this portion? Tries to erode. కొట్టి తీసుకెళ్ళిపోద్ది. దాని మన హై వెలాసిటీ వస్తుంది, ఫ్లూయిడ్ కొడుతుంది, తీసుకెళ్ళిపోతుంది. సో కొంతసేపటికి ఏమవుతుంది, సర్ఫేస్ అంతా పీల్ ఆఫ్ అయిపోతుంది. Clear? So let me stop here.